First thing you need to do when you open a spreadsheet is to go straight to the settings of the spreadsheet. The Analytic tab and the Numeric tab actually require different settings. The first tab you're going to work on is Analytics, so you need to make sure the settings are correct for that. They won't be correct for the Numeric tab, and we need to change it when you work on the Numeric tab. So if you go to File, Options, Formulas, these are the settings we need to check. It needs to be set on automatic, as this one already is, and we'll be changing that when we move to the Numeric tab. The other settings would be to have manual recalculation and iteration, but we want to have automatic. You may get a warning if you set it for automatic. You may get a warning that you've got circular references. You can just press OK and carry on through. That warning applies to the Numeric tab. We've been over the objectives for the work. It's not just for you to be able to predict contamination distributions in sediment, which is useful in itself, but to give you experience and understand what an analytical solution is, and also to implement a numerical solution and understand the difference between the two by comparing their outputs, calibrating both and comparing them. And then from that you can recognize how a numerical solution can allow lump parameters to become more specific and thereby improve the model. So they're the things you're looking at for to be able to do. The rest of the information is described in the Poisson equation, its derivation, and also the situation of the site where the contaminated sediments are, and the specific reasons for wanting to examine the porewater profile and why we would like to model it. So we can move to the Analytic tab. This is where you're going to be putting your analytical solution to the Poisson equation. That will require some parameters to be entered, and these have been entered for you already as constants in the top left corner. So we've got these constants: the recharge, the diffusion coefficient, and the depth. We've also got percentage water. Because you'll be using these constants in the equation, it's sometimes easier to give the cells names, in which case you can use a word in the equation which is easier to understand. So in this case, if we click on the recharge, the cell is actually named recharge rather than just B3. The name is an absolute reference. You can continue to use B3, and if you use it as a constant you need to remember to make it an absolute reference. If you call it recharge, then you don't need to make it an absolute reference. So we have recharge named, and we have diff K named for the diffusion coefficient, and we've named depth L. To change the name or to write a name in the box, you go to the name box and either delete the name that's in there or just write the name in that you want to have there, and then you press enter. When you press enter, that cell will be named what you've called it. The reason why we've got percentage water is that the diffusion coefficient, which we've taken from Lee and Gregory's paper for the free water diffusion coefficient, the diffusion won't be taking place in free water because it's taking place in the sediment, and the sediment is only 50% water. So we need to change the diffusion coefficient, and all we're doing is multiplying the diffusion coefficient by the percentage water, and that's how we get the effective diffusion coefficient. Now we can enter the equation. The only other thing we need now for the equation is x, which is distance, but for the Poisson equation, we actually need to have the total depth minus the depth that we're measuring at to give us x. We can copy that down. So now we have our values of x, and we have the parameters in the equation. We can enter the equation. Is equal to recharge divided by 2 times the diffusion coefficient L being the depth. Okay. Okay, and that's automatically updated the graph. Given that we've got the diffusion coefficient from the literature, and we've adjusted it by the average water content, then that leaves us with recharge, which is unknown. So you can calibrate by changing the recharge. So by changing the recharge, you can see how well you can get the model line to fit the observed line. When you've had a play with that, you can move on to the introduction to the numeric solution. Assumptions of the analytical model are actually incorrect, particularly the water content. The water content does vary with depth, and if the water content varies, then so does K. In the analytical, we just had one average water content. We know that at the top of the sediment pile it's almost 100% water, and by the time you get down to the bottom, it can be as little as 30% water. So that changes throughout the sediment pile, but that's not accounted for in our analytic model. The analytic model isn't able to do that. There's only one K value that can be put in. In order to incorporate this variable K, we need to use a numerical rather than an analytical solution. What you're going to do is to implement a finite difference form of the Poisson equation. That's a numerical solution, a finite difference form. R may also vary with depth, and you can change both of them with depth. The assumptions are otherwise very similar. There's going to use the same free water diffusion coefficient, but it's going to be changed according to the water content. The water content has been measured at different depths, so we can use the water content to adjust the diffusion coefficient. The other assumption is that the sediment was sampled to its full depth, which for the analytic solution meant that L equaled 39 centimetres. In the case of the numeric solution, it means that the way we treat the bottom cell is that we set it as a no flow or no diffusion boundary, which actually means it acts like a reflection at the bottom of the pile. We can move on and look at that now. If we click on the numeric, first thing we need to do is to go to settings, so options and formulas, and now we need to implement manual recalculation and iterative calculation. In order to implement the numerical solution using a computer, it's necessary to program the computer. A computer program is typically a combination of having variables, which are stores of data that can be manipulated and changed, conditionals, which allow comparisons of variables, which then control the action. The result of the comparison controls the action, and loops that repeat subject to these controls. So we have variables and conditionals which compare variables, and loops which just repeat actions and over and over again, controlled by the conditionals. And all of this is carried out very fast. So there's only a very few fundamental things that go on in a computer program. In the case of this exercise, Excel can be used to carry out one of the main jobs of a program without actually writing anything. You won't actually have to write a program for this. It's already written effectively in the background in Excel. And the thing that you'll be doing is repeating something until a condition changes. So that's having a loop that goes on, and it's going to continue until a condition is met. In order to use this feature of Excel, you do need to change the settings, which is what we've just done, which is to go to File, Options and Formulas, and then tick for Manual Recalculation and Iteration. That's the repeating part. So manual recalculation and iteration means that a set of calculations will repeat. They'll go round and round and repeat themselves. The setting of maximum change monitors the condition to decide whether to stop the repeating calculation, and we can just look at that again. We go to File, Options, Formulas. We've ticked Manual. we've ticked iterative calculation, and we've got maximum change and the number of iterations. So it'll either go through 100 iterations, or it'll stop repeating the calculation when there's no number on the spreadsheet that is changing by more than 0.01. So we have the constants that are required for the Poisson equation. We've got the production rate and we've got the diffusion coefficient. But we need to consider the form of the finite difference version of the Poisson equation. We're doing this because we've spotted that most areas aren't circular, and that's why they're not suitable for 1D models. And even if we look at a vertical profile, then actually most vertical profiles, or most profiles, are not homogeneous either. So we need to make them more specific, and we can't do that with the analytical solution, but we can do with the numerical solution. The numerical solution takes continuous spatial change, in this case in concentration, and discretizes it into many discontinuous changes. So instead of a continuous change of concentration with depth, we have change in concentration at particular points or particular cells with depth. And that means the differential equations can become difference equations, and the calculus becomes arithmetic, and lots of arithmetic, which is the thing that computers are pretty good at. The finite difference version of the Poisson equation tells us that the concentration in a cell is effectively the concentration above and below it divided by 2. It's the average of the concentration above and below. However, there's also the recharge to consider, so it's the concentration above and below plus the recharge divided by the diffusion coefficient, and all of that divided by 2. dx is the cell size, which again we've got written into our constants, and you can see that in this case the cell depth is 1 centimetre, so it doesn't actually change the equation. You can see cell size, centimetres 1, production and diffusion coefficient are written in there. We're going to be referring to those when we write the model. Enter the equation. Okay, we're going to have the cell above plus the cell below plus the cell depth times the recharge divided by the diffusion coefficient. In this case it's called T because we can't use diff K again. I need to put one more bracket around there. So that'll be the equation that takes the value of the cell above and the cell below and adds the recharge divided by the diffusion coefficient, and then we need to divide that by 2, give the average of those two cells.